Symposium. I didn't know exactly what I should say here, so I changed my title in the way that Fano would approve of, I think. And that's a Fano student strays into precision measurement in cold antihydrogen. Ugo was always intensely interested in my work after I left Chicago, but he always seemed slightly bemused by it and wondered if one could really, earn a salary doing these sorts of things, because there was no motion on a saddle or anything like that. Ugo was not my official PhD advisor. We never wrote any papers together, and I certainly never ate anything that touched his black toaster oven in his office, for those of you who remember that. But I know some of you did and survived it. I frequently... It makes you strong, yeah. And he always wondered whether my research topics were what he had really prepared me for. But I'm very grateful to Ugo Fano. In fact, I remember vividly the first time I first met him. I had some theoretical ideas, and my thesis advisor couldn't really comment on them very much. So I knew there was this famous guy at Chicago who did this sort of stuff, and so I screwed up my courage as a beginning graduate student, and I went into his office and said, I have some ideas I'd like to ask you about. And, Fano's a gentle guy. He absolutely destroyed me. He just, I was almost in tears. In fact, I think he even said some things that in retrospect I have a hard time believing Fano would say. Things about experimenters should stay in the lab and not mess with theory. They should leave it to, things like that. So I went home and I was crushed, okay? And then I thought about what he had said, and by golly, I thought I was right. And then I didn't know what to do. I didn't think I was up to going back in there again. And it took me a few days, and I went back in, and with great fear, I said, Professor Fano, I have a few more questions about this. I think some of the arguments I was making I didn't make so well, but I think they were right. And he graciously took me in, and we talked about it, and I think I persuaded him, and things went very well after that. And he was extremely accessible throughout my whole career. Now, that's my version of the story. Years later, his wife told me a different version of the story. Okay? She swears this was true. She said she remembered the day that he had first talked to me, because he came home and said, I met this interesting student today. I think he's going to do good things with me. And it was a very different point of view. So I don't know. But I'm very grateful to Ugo, and I certainly do not succeed in emulating the way he's willing to give time to his student. He was willing to give time to students, even those not in his group all the time. And I think he set an example for all of us to follow. I should warn you, when I give this talk, Ugo once told me he only counted me as half a final student for all of these reasons. So it's Now I was trying to think of what I could say that somehow bear relevance, and Ugo frequently sat me down and talked to me about saddles and things. So I tried to think of all the saddles in my work, and so I thought of two. Okay, and so I'm going to start out talking about saddles. The first is a Penning-Yaffe trap saddle in the most recent theory I've been involved in. I'm an experimenter, most of you know, not a theorist. So now I have to do two hands here. Okay. And so this is actually a saddle orbit, not a saddle potential. And then I'll tell you about the nested pinning trap, where a kind of saddle in the middle is the key thing, and it's actually causing us a lot of trouble right now, and we have to learn more about it. The issue having to do with the saddle orbit is the issue of, if you'd like to make cold antihydrogen, one thing you'd like to do after you make it is to capture it. Okay, and you'd like to hold it in a neutral particle trap of the sort some of the experimenters in the audience are well acquainted with, say a Yaffe trap. Of course, to make the antihydrogen, we first have to have positrons and antiprotons in pinning traps nearby, and let them talk to each other and persuade them somehow to form antihydrogen. So ideally what we'd like to do is we'd like to have a pinning trap for the charged particles, and in the same place in space we'd like to have a Yaffe trap or some such for the neutral atoms. That way we could catch everything at the same time and work efficiently with small numbers of particles. Now, we know about pinning traps pretty well nowadays. Okay, this is an old subject. There's axial symmetry in a pinning trap. There's a magnetic field, and there's an electrostatic quadrupole potential, which has symmetry around the axis made by the magnetic field. And there's a confinement theorem, which is basically having to do with conservation of conjugate angular momentum because of the nice axial symmetry. And the orbits are very familiar. There's the up and down axial motion. There's a circular cyclotron motion, this tight little circle here, and then there's a big magnetron orbit. And these, as I said, are well known and understood and have been for many years. Now, if we add a radial Yaffe field, let's just put 4 current bars in the conventional configuration, and let's not worry about the pinch coils at the end, because we can move those out to infinity after all. Well, we clearly destroy the axial symmetry. You know, it's manifestly not symmetric about the orbit. And in fact, our goal would be to make as deep a trap as possible, so we'd run absolutely as much current through these bars as we could, as close as we could, because the magnetic moment of a hydrogen atom or an antihydrogen atom is not very large. Okay. And so we destroy the axial symmetry, so there's no confinement theorem. So there's a question, are there any stable orbits in this configuration? And the answer is yes, there are these saddle type of orbits. Okay, if you look at this orbit and this one, they look quite the same, and they maintain their same features. Now, this is a theoretical result. It's not been tested experimentally yet, at least not in a parameter space close to what we use. And so this flat disk turns into the saddle, and it makes a kind of orbit. Now, how does one get at this? Well, there's the orbit again, and you have to do some awful stuff with all these equations and little factors and perturbation theory and so forth. And I don't know that Fano would like it so much, because this is all classical. I guess he didn't really like classical mechanics. But he didn't mind it if that was the only choice. But I certainly remember him sitting me down from time to time and telling me that if I didn't like quantum mechanics, I should get therapy, not write papers about it. I think that was his point of view. And maybe some of you have run into that too. But this we can only really do classically. And so you can work out these equations for these different frequencies. And again, they're the same basic frequencies that you have in a pinning trap. But they're modified a bit, okay, because you don't have the nice orthogonality that you have in a pinning trap. You can also work out what the orbits are, and there's a series. This is kind of a classical perturbation theory. And again, you get a cyclotron orbit, you get an axial orbit, you get a magnetron orbit, the same basic sorts of things, but the Fourier spectrum is much richer for each of those orbits. And in fact, if in keeping with the sort of thing Fano always stressed, you can make a picture of why this saddle orbit comes about. This outer cone-shaped thing is the equipotential in a pinning trap, and this sheet that goes through it is something we call the force-free sheet. Okay, if you write down the simple equations of motion, you can see there's a restoring force to either side of this sheet. And so the saddle orbit is actually just running around on the intersection of where you have conservation of energy and you have this force-free sheet. In my experience, Fano always loved pictures like this. Now, there are some resonances, just to get into the technicalities of it, because in this case, there's nice orthogonality between all the motions. The motions really don't couple, okay, unless you do something to make them couple. In this case, the orbits are not perfectly uncoupled. And that means you have to worry about resonances. That is to say, if one of the frequencies here, say omega z, is an integer times omega minus this other orbit, the two motions can couple. It's a kind of resonance of sorts. And the exact condition here, and because of the symmetry, there's a factor of 2. The moral of the story is you have to avoid these resonances in this sense, but if you do, it seems like, at least for small numbers of particles, okay, there's a one charge in a pinning Yaffe trap, you have stable orbits. So that's very encouraging. Okay, now even though there's no axial symmetry and no confinement theorem, there are adiabatic invariants instead, and they fill the role. Okay, and I recall learning about adiabatic invariants from Ugo as well. And this applies then to low-density single-component plasmas of particles. Now, of course, what about a large-density single-component plasma? There, I think the jury is still out on that one. whenever you have collisions, collisions are very effective at breaking down adiabatic invariants. And so somewhere, what I've told you isn't going to be true anymore if you put enough particles into that space. Right now, I don't think we know where that is. But we have some hope, and there are some people who are considering this more. Now, the second saddle that I'd like to mention has to do with the challenge we have of getting positive charge particles, positrons, let's say, to interact with negative charge particles, okay, antiprotons in our case, to make antihydrogen atoms. And we like to use these pinning trap wells. Well, if I make a well for the positive particles, the negative particles see that potential as a hill. Okay, and so it's a little challenging then, or you have to do something to get these particles together. And so what we've been pursuing now for a while is we make what we call a nested pinning trap, or a nested well. And actually during the night shift, just a night and a half ago, or I guess I'm sort of not sure what time I'm on, this is what we were working with. And so we have a well, a potential well that looks like this when you go down the axis of a pinning trap. And the magnetic field is also along that axis. There's all sorts of electrodes. The details aren't so important. Their role is just to allow us to make this kind of potential. And so the idea then is to put, well, let's do it with the interesting species, positrons in here and put antiprotons up in this well. Spatially, they're still going back and forth through each other. Okay, so they're free to interact. Okay, but in terms of the potential well, they have their own region of space where they want to be bound. Now, the saddle that happens is really in this region, and the interesting features actually go down to the interface. Because now, let's take an antiproton, for example. It'll go back and forth, it'll collide, and it'll drop down. And so you might think that it'll come right to the level of the positrons, okay, because the positrons are sitting in that well. And that's, in fact, what happens. Okay, we showed that some years ago with electrons and protons. But closer look shows there's a lot of interesting activity going on there, which we don't understand. Okay, and imagine an antiproton coming through. It goes fast through here, and then it slows down. And when it's going very slow, that's when it interacts with the positrons. Now, that's good for making antihydrogen. But it also gives you a long time to have collisional interactions, okay? And the collisional interactions can cause you a diffusion on this sort of hill, okay? And the diffusion on this hill doesn't seem to always be our friend. More about that in a little while. Okay. Here's the first demonstration of positron cooling. We put positrons in a well. This is the same picture I just showed you turned on its side. Okay, the positrons are here. Antiprotons are initially in this well. We lower this little peak to load the antiprotons in here. So we take cold antiprotons and we make them hot with respect to the bottom of the well, or at least we give them a velocity. Here's the spectra that we see if we just take this potential bump and ramp it down to let the particles spill out. Okay, that's a kind of energy analysis that we can do. And you see, without any positrons in, we see these very, hot antiprotons, so I colored them red. Hot is only 6 volts, but we can make them as hot as we like. We can move them up to a much higher energy if we'd like, just by deepening the wells. And then if we put positrons in, we see some of those left, at least in the first demonstration. That doesn't happen so much anymore. The reason there's some left is as the positrons go back and forth, as the antiprotons go back and forth through the positrons here, the radius of the antiproton cloud was bigger in this case, and so not all of them, those with big radii, didn't interact with the positrons, and so they weren't cooled. Okay, now, there's a little peak, and if you look at this closely, it's actually a double peak. That's the curious thing that happens, where the positrons are. And then over time, a longer time scale, about 10 times longer, about 10 seconds, you see this sort of distribution happening as you go to lower energies. Now, this is evaporative cooling, okay? And it's a kind of recycled evaporative cooling. And I'm getting so that I hate evaporative cooling. You'll get the theme of this in a little bit. What happens is an antiproton can collide, a hot antiproton in this well, okay, in the distribution, can pop up, just like in the normal sense of evaporative cooling. If it does, it then is free to collide with the positrons. Okay, and the positrons will cool it back. So it's evaporative cooling without loss. So that's a good thing, kind of a recycled evaporative cooling. The bad thing is that there also seems to be, in some circumstances, and we don't have it all nailed down yet, so I can't be positive that what I'm telling you is true right now, but in some circumstances, the antiprotons from the evaporation seem to come out of our trap radially. Okay? And that's a bad thing, okay, for us, because it makes backgrounds in our detectors. Okay, and we have no good way to monitor it except in the destructive sense of seeing the particles after they left. We're trying to solve that problem and figure out how to minimize it now. Now, if you look at the positron cooling time constant, it's about 1.4 seconds, and it's a nice exponential. So these antiprotons just come down, colliding with the positrons. It works very well and very efficiently. If you get too curious, oops. I have copies in here. Oh. This never happens with, there we go. If you look curious, if you get curious and you look at the time constant and you look at the energy of the antiprotons as a function of time, as you go along that 1.4 seconds and beyond, okay, then you see there's a much richer structure than the simple exponential shows you. Here's the energy spectrum. This is high energy on this end, low energy on that end. This is the peak where we launch the antiprotons. As time goes on, this peak slides down, but there's a bunch of structure, and then you eventually get this low energy peak here. Now that's a little difficult to visualize, so we made a movie. We start out with an initial distribution, and then that distribution slides down. Okay, the 10 millisecond clicks are happening here. Okay, and it goes down. Now the positron level is here, and you get this peak here, and then there's another little peak on the other side that develops. Okay, so a lot of actions here. And then if you wait long enough, this slowly, now the evaporative cooling, recycled and perhaps with loss as well, okay, radial loss, this is happening. You see the evaporative cooling happening, and eventually this distribution will end up down here. Though I won't wait to go through all of the slide here. Okay, now what are the motivations? The motivations are the sorts of motivations that Ugo Fano always listened to me when I talked about them, but he never warmed to them in an appreciable way. Okay, reality is invariant under symmetry transformations. We thought it was invariant under parity transformations, and we thought it was invariant under charge conjugation and parity. And now, because we were wrong twice before, we're even more sure that CPT is a good symmetry. But we have to test it experimentally, and that's what we're about. We'd like to really go ahead and see whether antihydrogen and hydrogen have the same spectroscopy. And that's what we're after. And if so, that would be a confirmation of CPT symmetry, at least in that system. Now, cold antihydrogen atoms are what we're after. Some hot antihydrogen atoms were seen some years ago, 9 of them to start, and it made a huge public relations thing when it happened, okay, especially in Europe. I spent 2 days here at Harvard, even at home. The reporters found me at home, talking to European reporters mostly, okay, when this happened. And it wasn't my experiment. But there's no really hope to do hot antihydrogen experiments that have any precision, because the antiprotons, the antihydrogens fly back very quickly. You can't measure with any accuracy. And so if the goal is to do accurate spectroscopy, accurate comparisons of antihydrogen and hydrogen, we really have to trap the cold antihydrogen to do the spectroscopy. And that's really been a goal that we have been after for a large number of years, okay? And there's many steps, of course, that are involved. The collaboration that I'm privileged to lead right now, the current members are shown here, and from several institutions. We run at CERN for about half the year. Antiproton beam time is very precious, and so for half the year you'll find me there generally every week. It makes life interesting. What our goal is to get a very high precision in the comparison of the antihydrogen and the hydrogen. Here's orders of magnitude of accuracy, parts in 10 to the 4, 5, 6, and 7. A measurement we did where we compared the charge to mass ratios of the proton and antiproton is the most accurate baryon CPT test now. A lepton CPT test done by the Seattle group is the most accurate test of CPT with leptons. We are right now in a lab that you can see during ICAP, if you wish, have a one-electron quantum cyclotron, and we're pretty excited because we think we can push this down another order of magnitude using that device. The best hydrogen 1s, 2s spectroscopy, it's actually a little further down now, is in this region. And some people dream, not me, I'm going to be retired by then, and I don't intend to retire, okay, think you can get an accuracy down here. But we think we can get a much higher accuracy than the baryon and lepton CPT tests. Now, if we compare the Rydberg and the anti-Rydberg for hydrogen and antihydrogen, what we would be comparing is really the mass and charge of all the constituents, all the ingredients. So there's good news and there's bad news in there. The good news is we'd be sensitive to any differences between the matter and the antimatter counterparts, masses or charges. The bad news is if we do see a difference, we won't know which one it is. Okay? But, you know, I'll deal with that problem later. That would be a wonderful problem to have. Okay, now what are we doing? I'll try and just give you a verbal report of the sorts of experiments we've been doing so far. There's a large number of mechanisms. I don't know if I even have all of them on. I think I probably have them all on. Different ways to make antihydrogen. And frankly, I don't know which one is going to work. Okay, they're all very difficult. And they're difficult because if you have enough energy to get the proton, the antiproton and the positron together, you need to carry off the energy somehow to make the bound state. And so you need another body that's involved. Okay? And getting the other body involved is difficult, especially since it's an antimatter species typically. Now, radiative recombination uses the photon as the third body. So you make an excited hydrogen atom or antihydrogen atom and you radiate the photon. Just as we speak, or it just finished a few hours ago, we have been trying to do this process. The problem with this process is the rate is very low, okay? And so it's not so easy. You can stimulate with a laser. If we're very lucky, later this year we'll be able to try that. We have another apparatus that's being assembled right now which will allow us to do that. But we're still working in a space which is very small, and it's not really big enough to allow us to get the lasers and stuff in. We have a bigger apparatus that's being assembled, but the main part of it, a huge solenoid that's been on order for a number of years. It's 2 years behind schedule now in the shipping, and hopefully it's going to be shipped in 3 weeks, but we have heard this story before. You theorists don't have to deal with that kind of thing, but superconducting solenoids are a pain in the neck. Okay. But we'll hope to be trying this later this year with the CO2 laser. This is the process with the biggest rate. And that we've been trying. The problem here is you make Rydberg antihydrogen, which is very delicate. And even though we've likely made some, we've not yet been able to do it in such a way that we can see it. Okay? We thought we had it last fall. We set up better electronics and experimental technique as we had to before we announced it. And so far, at least this year, the signals we were seeing are sort of elusive. We haven't been able to confirm that, and we're not exactly sure why. So we're still pushing on that. There's a field-assisted recombination, which works much like the way we trap particles. What you do is you have a tilted Coulomb potential from an electric field, an antiproton and a positron. When a positron comes in and turns around, you snap the door shut by turning off the field. Okay? And we actually were looking for that pretty hard. We stopped when we saw this signal that we thought was three-body recombination. It was just much bigger than what we could see here. And so we discontinued it. We may go back to that now. Another method that's been proposed, we aren't doing in this form, but you take an antiproton plus positronium, then the electron can conserve energy and momentum, and the positron gets captured. The problem, again, with this process is that the rate is very low. Well, we did push it a little bit, but in this form, if you take an antiproton plus positronium, but in an excited state, just to make the cross-section bigger, okay, then you have a better chance at it. And we actually tried an experiment like that 2 nights ago and didn't see a signal. But again, the rate is still very low. I mean, in this case, we were looking for 100 antihydrogen atoms to be made in 16 hours. Okay, and you really have to have your backgrounds under control if you want to do that. And we're learning that, but it's taking some time. Another process that we're pursuing right now, and the apparatus for half of this you can see at Harvard if you visit the lab, we excite a cesium atom into a Rydberg state with a pair of photons. And then we let that cesium atom charge exchange with trapped positrons, okay, to make positronium. Now, we haven't published this yet, but we have demonstrated this. The event rate was low, and we know we can do better, so we're redoing the experiment. So half of it's done. So then we would have Rydberg positronium, which we could charge exchange with trapped antiprotons to try and make the cold antihydrogen. So it's sort of democratic here, at least from my point of view. I don't care which of these methods wins as long as we manage to make enough antihydrogen to do cold spectroscopy.
In your first radiative recombination, is that the presence of a magnetic field?
Yes.
You have a magnetic field in radiative recombination?
Yes.
We do have a magnetic field there.
How big is it?
It's 6 Tesla.
Okay.
But it doesn't matter so much because the radiative recombination is mostly down to the ground state where the field doesn't make as much of a difference. Okay. The field is much more important for the three-body case. Okay, it's dominant, in fact, and that's one of the challenges we've been working with. Okay. I think I'm going a little more slowly, probably because I got a little nostalgic about Ugo. Let me just, it's all right, he deserves it. Let me just mention a couple of things. What is the effect of the electric and the magnetic field, as your question suggested? That's a huge issue here, okay? And we're just still learning that way. If you even look at a trajectory calculation for the particles, these don't look like your ordinary atoms, okay? And they don't form in the same way, and the cross sections aren't the same. So your intuition on what the sizes of things are, at least mine, is not so good. Oh, I went too quickly. Okay, and there's also plasma effects because we're trying to get a high density of particles together. Okay, and so the collective effects can be very important. If you're not careful and you excite a plasma mode inside of these clouds, you can lose all of your particles rather than having a more efficient mechanism for production. Okay, let me just conclude then, since my time is about done. Where are we right now? Well, we need cold antiprotons, and we have those. I mean, it's now a robust thing, and it's sort of wonderful. There's this AD facility, the antiproton decelerator, that's been built at CERN, at a particle physics establishment, just so these experiments can go on. Okay, that's a remarkable thing in a time when CERN is scrambling to save its particle physics life, okay, because the LHC costs so much. We need cold positrons. Those we load from a radioactive source by making Rydberg positronium, okay, and then ionizing the Rydberg positronium. There are a lot of interesting issues there, too, even involving possible quantum reflections that happen inside of the material when you make the cold positrons. We need the antiprotons and cold positrons in the same structure, and we have that now. We can do this robustly. And we need an interaction, and we've been able to see that. We saw intriguing signals we thought were antihydrogen. Right now, it doesn't smell right, okay? And so we're still investigating it, and we'll have to see what happens. There's still a lot more that has to be done, okay, because the goal, of course, is the spectroscopic comparison of antihydrogen and hydrogen. And we have laser systems that are under development, new apparatus that's being built and assembled and so forth. One has to do a lot of this stuff in parallel, even before you before you invent your way to the intermediate conclusions. So that's all I have to say. Again, thanks so much for inviting me, the organizers, to give tribute to Ugo Fano. He had a tremendously large effect on my life. I hope that I occasionally affect a student at a fraction of the influence that Ugo had on me, because then my career probably will have been worthwhile. So, thanks.